Welcome to the second lecture of the fourth week of Lent term. And last time we started chapter 5, and the first thing that we learned in this chapter was this division algorithm, which is really a theorem which says that if you have any two integers m and d, where d is not equal to 0, you can divide this m by d, and in the process you get a quotient q and a remainder r, so that m is equal to qd plus r, and this r, remainder r, is bigger than or equal to 0 and strictly less than mod d. Then we talked about divisibility, and then we introduced this greatest common divisor of a pair of integers. So that's a positive integer, which is a common divisor first of all, so it divides both a and b. And moreover, it's the greatest one in the sense that if you have any other common divisor d of a and b, then this d divides this greatest common divisor. And we saw that if the two integers are both equal to 0, then the greatest common divisor does not exist. But in every other case it does, and we proved this theorem which says that if a and b are two integers which are not both 0, so at least one of them is non-zero, then the greatest common divisor does exist, and moreover it can be expressed as a combination of a and b with integer coefficients. So there exist integers x and y such that this greatest common divisor is ax plus by. This equation is called the Bezout equation, and we saw that it has lots of solutions. Then we discussed the Euclid's algorithm in a specific example. So this was based on the following lemma. So this lemma says that if you have two integers a and b, where a is not equal to 0, then no matter which integer x you take, the greatest common divisor of a and b is the same as the greatest common divisor of a and b plus ax. So to this b, I can add any multiple of this a, and the GCD does not change. And we use this lemma to calculate the GCD of two integers. And while that example used concrete numbers, the plan was today to begin the discussion by talking about the general Euclid's algorithm, how one proceeds with that. And today we will also discuss relatively prime or coprime integers, and finally we will also begin our discussion about the prime numbers. So that's the plan today. We will now formalize Euclid's algorithm for computing the greatest common divisor of two integers. Now first of all, last time we saw that we can put minus signs in front of these integers without changing the GCD. So we can assume that both of them are non-negative, and moreover if one of them is 0, then we know that the GCD is just the other number, and so we may assume that both of them are positive. Also, if the two numbers are equal, then the GCD is just the number, so we may assume that one of them is bigger, and since we can swap the two entries, it's okay to assume that the second entry is strictly bigger than the first entry. So we'll learn to compute the GCD when the two integers are such that b is strictly bigger than a is strictly bigger than 0. And we also know that to b, if I add any integer multiple of a, the GCD does not change. This was the lemma that we just mentioned, and this is the key lemma which is used in this Euclid's algorithm. So the first step is to divide the bigger number by the smaller number, and in the process we get a quotient and a remainder, and this remainder is bigger than or equal to 0 and strictly less than a. So now there are only two possible cases. Either this remainder is equal to 0 or it is not equal to 0, in which case it is strictly positive. Now in the case when it is equal to 0, let's see that we are actually done and the GCD is simply the number a, and the reason is because to this b I can add this integer multiple of a, but b minus q1a is exactly r1, so this is r1, and r1 is equal to 0 because we are in this case, so you get GCD of a comma 0 of this positive number comma 0. So that's just this positive number, we saw that last time. So in this case we have found the GCD, and in the other possible case is when this r1 is positive, in which case if I do the same thing, then I again end up with GCD of a comma r1, and then I can swap these two entries, so I have got GCD of r1a. Let's first note that this number is smaller than this number, just like as we had before, and now this r1 is strictly smaller than this a, and this a is strictly smaller than this b. So we have got a new pair of integers, a prime and b prime, which are both positive, and moreover this is strictly smaller than this one. And then we can repeat this process where we divide this new b prime by a prime, get a quotient and a remainder, then again correspondingly we will be in case 1 or 2, and if we end up in case 2, we can then again repeat the process and so on. So we have to show that this process terminates at some point. Now we know that the process terminates if we end in case 1, and if we are in case 2, then we can repeat the process, because then these two are positive and you can divide the bigger number by the smaller number. So we have to show that we cannot keep getting case 2 infinitely many times. So we can get case 2 at most a finite number of times. So to show this, let us look at what happens to the sum of the two arguments each time you end up in case 2. So the seed sum is this capital N, which is defined to be A plus B. Okay, so you take the two arguments and you add them up. Let us show that we cannot get this case 2 more than this capital N times. Because if you start with this, then the updated sum of the two arguments will be this capital N prime, which is this new A prime plus B prime. But we know that A prime is this R1, which is strictly less than A. So this R1 is at most A minus 1. And this B prime is really A, and A we know is strictly less than B. So it is at most B minus 1. And A plus B is what we had called this capital N, and then you have this minus 2. So the updated sum of the two arguments is less than the sum you started off with. In fact, it is less than or equal to capital N minus 2. Now, if we keep getting case 2, then what happens to the sum of the two arguments? You started with capital A plus B, but then there is a reduction of 2, there's a further reduction of 2, a further reduction of 2, and this process cannot go on forever. In fact, after capital N steps, you will have that in each step there is a reduction of 2. So in capital N steps, you will have a reduction of 2n. So the sum of the arguments will then be minus capital N, which is negative, which is absurd because these are a natural number. So it cannot be less than 0. And so the process cannot have more than capital N steps. So it has a finite number of steps. Okay. So the process certainly terminates, and then we will end up in case 1, and then we have found the GCD. So let us make this a little bit more clearer. So suppose that there are n steps, and at the nth step we reach case 1. Okay, and let's see why then we have found the GCD. So to explain the process in general, when there are n steps, let us make the observation that whenever we end up in case 2, we are then continuing the process by dividing the A by the remainder just found. So we are dividing the A by the remainder just found. So we'll now explain Euclid's algorithm abstractly by assuming that there are n steps that one gets, and we in step 1 begin by dividing the B by A. You get a quotient and a remainder, and then in the second step we divide this A by R1 and you get a quotient and a remainder, and we continue in this manner up till at the n minus first step the previous divisor we divide by the remainder and you get a new quotient and a remainder, and finally at the nth step when we divide this by the remainder, then we get remainder 0. Okay, so we get this array, and we are assuming that in each of the steps we end up in case 2, and finally at the nth step we end up in case 1 when the remainder is equal to 0. So we'll now prove the claim that the GCD of A and B is the last non-zero remainder, that is the remainder at the n minus first step before the remainder becomes 0 in the nth step. So the GCD of A and B is Rn minus 1. So let's justify this claim. Now the GCD of A and B is not changed if to B I add any multiple of A. So the GCD of A and B is the same as the GCD of A comma B minus Q1A, where this Q1 is this first quotient. And we note that B minus Q1A is then just R1. So this is the GCD of A comma R1. And we can swap these two without changing the GCD. So this is the same as the GCD of R1 comma A. So we started with A and B, and now these are the updated A and B. So we are assuming that this R1 is not equal to 0. So we are in case 2, and then R1 is strictly bigger than 0 and strictly less than A. So we have got an updated A which is less than this updated B. And then we can continue the process. So we divide the a by r1, and then we know that the GCD of this thing is the same as the GCD of r1 comma a minus q2 r1, where this q2 is the next quotient that we get when we divide a by r1. And we note that a minus q2 r1 is this new remainder r2. So you have GCD of r1 comma r2, where if we assume that this r2 is again non-zero, so this r2 is bigger than 0 and strictly less than r1, then we can swap these two so that we have GCD of r2 comma r1. Okay, so we started with the a and b, and then we found an updated a and b, namely this r1 and a, and at the next step we have an updated a and b, namely this r2 and r1. And if we continue in this process, each time assuming that we are in case 2, then we end up at some stage with the GCD of rn minus 1 and rn minus 2. Now what we will do is we will divide this rn minus 2 by rn minus 1, and then we get the remainder 0. Okay, so this GCD is the same as the GCD of rn minus 1 comma rn minus 2 changed by a multiple of this rn minus 1, and the multiple that we'll use is this last quotient. So this GCD is the same as the GCD of rn minus 1 and rn minus 2 minus qn rn minus 1. And we note that this is nothing but 0. That's the last remainder. So we end up with the GCD of rn minus 1 and 0. And let's note that this previous remainder we had assumed was not equal to 0. Okay, and so it's a positive number, so it's a natural number, and we know that the GCD of any natural number comma 0 is that natural number that we had seen last time. And so this GCD is nothing but rn minus 1. So we have proved the claim that the GCD of AB is the same as rn minus 1, which is the last non-zero remainder in this process. Of course, this general process written out abstractly like this seems harder than what we did last week with a concrete example. So let us now revisit another concrete example and see this in action. Okay, so here is a concrete example. Suppose we want to calculate the GCD of 24 and 35. So we will divide the bigger number by the smaller number. In the process, we get a quotient and a remainder. And then to this 35, I will add this minus 1 times the first number, and the GCD does not change. But this 35 minus 1 times 24 is just this remainder, and then I swap the two entries so that you have the bigger number second. And then we continue the process. So I will now divide this 24 by 11, and then I get this quotient 2 and the remainder 2. And then to this 24 I will add this multiple of 11 with a minus sign, so then the GCD does not change, but 24 minus 2 times 11 is just this remainder 2. And then I'll swap the two entries so that this bigger number is second. And then I continue the process, so I'll divide this 11 by 2, and in the process I get this quotient 5 and remainder 1. And then to this 11 I will add minus 5 times this 2, so the GCD does not change, and 11 minus 5 times 2 is just this 1, so you have got the GCD of 1 and 2. And I continue the process, so I divide 2 by 1. Oh, but now we get the remainder 0, so the process is going to terminate. So we have that if I subtract 2 times 1 from this one, then the GCD does not change, but 2 minus 2 is equal to 0. And so I've got GCD of 1 and 0, which is equal to 1. So the GCD of these two numbers is equal to 1. And last time we had also mentioned that by solving for the remainders backwards, in other words, expressing each remainder in terms of the rest of the data, we can also solve the Bezout equation. So let's also see how that is done. So we know that the GCD of 24 and 35 is 1, and this 1 was the remainder over here, so that you express in terms of this. So this is 11 minus 5 times 2. But this 2 was the remainder over here, so that 2 can be expressed in terms of this data. So it's 24 minus 2 times 11. So 11 was the previous remainder, so let's collect out all the terms in 11. So you have minus 5 times 24, which I've written over here. 24, by the way, was one of the numbers, so that's good. And what's left over here is minus 5 times minus 2, which is 10, and then there's an extra 11 over here. So this is 1 plus 10 times 11. Now this 11 was the remainder here, which can be expressed in terms of the two numbers. So we do that and we write it as 35 minus 1 times 24 over here. And now we have got our numbers. We have 24 and 35 appearing, and so we collect out all the terms containing 24 and all the terms containing 35. With 24 I get minus 5, and then 11 times minus 1, so you have minus 5 and minus 11. And with 35 I get 35 times 1 plus 10. So I've got a times an integer x plus b times the integer y, where a and b were our original numbers 24 and 35. So we have expressed the GCD as a combination of the original numbers with some integer coefficients. Okay, so this can always be done by writing the remainder in terms of the other data, and you keep going backwards till you end up with the old numbers. Now in the previous example we had two integers whose greatest common divisor was 1, and such integers are said to be relatively prime or coprime. So here is the definition. If a and b are two integers, then we say that they are relatively prime or coprime if their greatest common divisor is equal to 1. So as an example, the previous integers we considered, 24 and 35, are coprime because we have seen that their greatest common divisor is equal to 1. So here is a theorem about these coprime numbers. So if you have two integers, then saying that they are coprime is the same as saying that there exist integer solutions x and y to this equation, ax plus by is equal to 1. So a and b are coprime if and only if there exist integers x and y such that ax plus by is equal to 1. So let's prove this. Let's start with the if part. There are two implications here. If this happens, we want to show that a and b are coprime. So we know that there exist integers x and y such that ax plus by is equal to 1. And now we want to show that a and b are coprime. In other words, their greatest common divisor is equal to 1. First of all, let's note that in this equation, you cannot have both a and b equal to 0, because then this left hand side will be 0 while the right hand side is equal to 1. So we know that not both of these integers are equal to 0, but then we know that the greatest common divisor of these two has to exist. So let's call the greatest common divisor of a and b, which we now know exists, as d. So this is a positive number, and this greatest common divisor, being a common divisor, certainly divides a and b, but then it will also divide any combination of a and b with integer coefficients. So in particular with these two integers, we will have that d divides ax plus by, but ax plus by is equal to 1. Now this 1 is non-zero, and whenever an integer divides a non-zero integer, the modulus of this integer is less than or equal to the modulus of this integer. But this is positive, so what we get is d is less than or equal to 1. There is no integer which is strictly bigger than 0 and strictly less than 1, so this d has to be equal to 1. Okay, so we have got that the greatest common divisor of a and b is equal to 1. Now let us show the other part, namely that if a and b are coprime, then this happens. Well, if they are coprime, then their greatest common divisor is equal to 1, but we had also seen that the greatest common divisor can be expressed as a combination of a and b with some integers. So we know that there exist integers x0 and y0 such that this greatest common divisor is ax0 plus by0, but this greatest common divisor is 1 because we are assuming that the numbers are coprime, and so you have got that there exist integer solutions to this equation. 1 is equal to ax0 plus by0, exactly as we want over here. So if they are coprime, then this equation is satisfied for some integers. So we have proved this theorem. We will now consider a sort of theoretical example, and the point of this example is to give a geometric interpretation of coprimeness. So suppose that you have two positive integers a and b, so these are natural numbers, and we are going to show that ab is coprime if and only if the following thing happens geometrically: that the point AB is visible from 0, 0 in this z times z. Okay, so on the x-axis, you have all the integers marked in as these orange dots, and on the y-axis, you also have the integers marked with these orange dots. And then we take the Cartesian product, okay, and that gives rise to this lattice of orange points. So for example, this is the point 1, 0, this is the point 1, 1, this is the point 2, 2, and so on. So we call this a lattice because it reminds us of a lattice of atoms. Okay, so but this set of orange points is this set z times z. Now it turns out that AB is coprime if and only if the point A comma B is visible from 0 0. So what do we mean by that? That means the following. Suppose you're here and from here you can look at these orange points. So the point A comma B is coprime if and only if it is visible from the origin, in the sense that if you join these two in this line of sight, there is no obstruction. So there is no orange point blocking the view. So for example, 5 and 4, you can check for yourself, are indeed coprime, that GCD is equal to 1. And here you see that if I join that to the origin, there is no orange point lying on it. So from this point, you can view 5, 4, 5, 4 without any obstruction. On the other hand, 2, 4, these two are not coprime. The greatest common divisor is 2. It is not equal to 1. And if you try to view 2, 4 from the origin, that is, in other words, if you join these two, there is an obstruction. There is this point, orange point, 1, 2, which lies on it. Okay, so indeed it seems to be true, at least in these two examples. But now let us prove this. Okay, so there are two implications to be proved. Let us first prove that if AB are coprime, then indeed AB is visible from 0 0. Okay, so suppose that this is not true. In other words, it is not visible from 0 0. So there is some point x comma y which blocks the view, right? So in this x is then strictly less than the a, the y is strictly less than b, and this is something which lies on this line which joins 0 0 to the point a comma b. What does it mean that it lies on this line? That means that if I look at the slope that I get when I use these 2 points 0 0 and the point AB, that's the same as the slope that I get when I use these 2 points. They have the same inclination. Okay, so that's what would mean that it lies on the same line. So in other words, b minus 0 by a minus 0 is the same as y minus 0 by x minus 0. But if I rearrange this, I get ay is equal to bx. And I'm assuming that this is not true, but this is true. So a and b are coprime. So that means that the greatest common divisor is 1. But then we have just learned that this 1 can be expressed as a combination of a and b with some integer coefficient. So we know that there exists x0, y0 such that 1 is equal to ax0 plus by0. Now I multiply throughout by y because I want to see the combination ay appearing here. Okay, so this step is a bit out of the blue, but let's see what we get. So if I multiply throughout by y, then I get y is equal to y times 1, of course, and this 1 is really ax0 plus by0. And now if I use the distributive law, I get ya times x0 plus yb times y0. Okay, and ya we know is equal to bx, ay is equal to bx. So if I substitute that, then I have bx x0 plus yb y0, and we notice that b is a common factor. So if I take that out, then I'm left with something. Now we wanted to get a contradiction because we assume that this is not true. So we are heading towards a contradiction, and we already see a contradiction appearing because this is going to be some integer, and we had started with this blocking the view. So we knew that y was something which was smaller than this height, right? So this y was smaller than this one. So we know that y is strictly smaller than b, but since this thing is a multiple of b, it's going to be sort of bigger in size than b. Okay, so we have got that y is equal to b times this integer, and we also know that y is not equal to 0 because this intermediate point is different from the origin. And so we know that since b divides this non-zero integer, the mod of b should be less than or equal to the mod of y. But both b and y are natural numbers, and so the mod of b is b itself and the mod of y is y itself. And so what we have got is y is bigger than or equal to b. But on the other hand, we knew that this point blocking the view is such that this y is not this point AB, and so this y is strictly less than b, but now we have got the exact opposite. So we have arrived at a contradiction, and this contradiction shows that there cannot be a point which blocks the view, and so we have managed to show that if AB is coprime, then the point AB is visible from the origin in this lattice. So let's now show that if AB is visible from the origin, then A and B are coprime. So first of all, since A and B are natural numbers, we know the GCD exists. Let's call it D. And let's assume that the two numbers are not coprime, so D is strictly bigger than 1. Now since D is the greatest common divisor, in particular it's a common divisor, so D divides A and D divides B, and so there exist integers x and y such that x multiplied by D is A and y multiplied by D is B. And moreover, since A and D are both positive, it has got to be the case that x is also a positive integer, so x is a natural number, and likewise y is also a natural number. Now we also know that D is strictly bigger than 1, that's what we are assuming. And then if I multiply both sides by this positive integer x, then we get x times 1 is strictly less than x times d, but x times d is a and x times 1 is x. So we get x is strictly less than a, and similarly y is strictly less than b. Okay, so what we have is b minus 0 by a minus 0. Now b we have just discovered is y times d and a is x times d. So we have that the d cancels and we get that this is y by x, which is y minus 0 by x minus 0. Now these two are positive numbers which are less than a and b. We have that the point xy when joined to the origin, that line segment has the same slope as the line segment one obtains when you join the point AB to the origin. So that means that this xy lies on the line joining the origin to AB. And so it cannot be the case that AB is visible from 0, 0, and this is a contradiction, and this contradiction shows that our original assumption that this greatest common divisor is strictly bigger than 1 cannot happen, and so this D is equal to 1. So A and B are coprime. So what we have shown is that the pair AB is coprime if and only if the point AB is visible from the origin. We will now show this theorem which we will use later on, and this theorem says that if A, B and C are three integers such that A and B are coprime and A divides the product of B with some integer C, then A has to divide C. So let's prove this now. Let A and B be coprime, and then we know that there exist integers x and y such that A times x plus B times y is the GCD of A and B, which we know is equal to 1. So we know that this is true. Also we know that A divides BC, so BC can be written as A times some integer q. Now I know something about BC, but I don't see the combination BC over here, so I'll multiply this equation throughout by C. So if I do that, the left hand side is AX plus BY times C and the right hand side is C times 1, which is C. And now if I use the distributive law, then I see BC appearing over here, but BC we know is AQ, so if I replace that, I get this. And we note that A can be taken as a common factor. So if we do that, then we see that C is equal to A times this integer. So A divides C. So we have proved this. And a corollary of this result is that if A and B are coprime and A divides B to the power k C, where k is some natural number, then A has to divide C. And a while ago, when we proved the rational zeros theorem, we actually used this. And over there we had given a heuristic argument, but we had said that in chapter 5 we will do this precisely using a result, and this was the result, and this is the corollary which we actually used over there. So let's prove this. If k is equal to 1, then what we have is that AB is coprime and A divides BC, but what we have just shown is that then A divides C. So the base case is fine. And let us suppose that we have managed to prove this for some natural number k, and now let's prove it for k plus 1. So we have that A divides B to the power k plus 1c, and this B to the power k plus 1c I can write as B to the power k times BC. So by the induction hypothesis, since A and B are coprime and A divides B to the power k times an integer, we know that A must divide that integer. So we conclude by the induction hypothesis that A divides BC, but now A and B are coprime and A divides BC, and hence by this theorem we must have that A divides C. So also in this case we have that A divides C. So by the principle of induction, then we know that this is true with every natural number k. So we have got this corollary as well. We will now discuss prime numbers. So here is the definition of a prime number. An integer p is called a prime number if first of all p is strictly bigger than 1 and the only positive divisors of p are 1 and p. So we know the prime numbers from elementary school, but let's use the rules that we have learned in the previous chapter to show that 2 is a prime. So let us suppose that 2 is equal to m times n, where these m and n are positive divisors of p, so they are really natural numbers. Now m and n can't both be 1 because then their product will be 1, which is not equal to 2. So at least one of them has to be strictly bigger than 1. Let's suppose that n is strictly bigger than 1. Then since n is strictly bigger than 1, if I multiply both sides by the positive integer m, the inequality is preserved, but m times 1 is m, which is bigger than or equal to 1, and m times n is 2, that's our assumption. So we have got this integer m, which is bigger than or equal to 1 and strictly less than 2. And one of the exercises was to show that there is no integer between 1 and 2 which is different from both of these. And indeed, if m is strictly bigger than 1, then m is 1 plus k for some natural number k. But then this 1 plus k is bigger than or equal to 1 plus 1 because k is bigger than or equal to 1, and you just add 1 to both sides. And so we get that m is bigger than or equal to 2, which contradicts the fact that m is strictly less than 2. So m can't be bigger than 1, and so m has got to be equal to 1. But if m is equal to 1, then n becomes 2. Okay, and so we are in this case that the only positive divisors are 1 and the number itself. And if m is strictly bigger than 1, then we just interchange the roles of m and n in this second case, and the same proof shows that in that case m is 2 and n is equal to 1. Okay, and of course we don't want to be giving such proofs every time, but we know what the first few primes are. They are given by 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on. So we will now show the theorem which says that if p is a prime and n is an integer such that p does not divide this n, then p and n are coprime. So in other words, a prime number is coprime to every integer that it does not divide. So let's prove this. We know that p is an integer which is strictly bigger than 1, so it's not 0, and so this greatest common divisor of p and n exists, and let us call it as d. Now since this is the greatest common divisor, it divides each of these numbers, so it divides p and it divides n. But now since this d, which is positive, being the GCD, is a positive divisor of this p, but p being prime, it has the only two positive divisors which are 1 and p. So this d has no choice but to be equal to p or equal to 1. Let's consider the two cases separately. If d is equal to p, then since d divides n, this just means that p divides n, but that contradicts this. So this case is just not possible because we arrive at a contradiction. So it has got to be the case that d is equal to 1, but that just means that the greatest common divisor of p and n is 1. In other words, p and n are coprime. So this proves this theorem. So once again it says that if p is a prime and n is any integer that p does not divide, then p and n are coprime. So we have just proved the theorem which says that if p is a prime number and n is an integer such that p does not divide this integer, then the greatest common divisor of p and n is 1. In other words, p and n are coprime. And now using this theorem, let us prove the following corollary, which says that if p is a prime number and n is any integer whatsoever, then one and exactly one of the following two statements holds. Either it's the case that p divides n, or it's the case that p and n are coprime. So we have this dichotomy, and let us prove this. So first of all, let's show that one of the two statements has to hold. So if one holds, then we are done, and if one does not hold, that means that p does not divide n. But then by this theorem, since p is prime and p does not divide n, it has to be the case that the greatest common divisor of p and n is equal to 1, which is exactly this second statement. And let us also show that these two statements are mutually exclusive. That is, if one holds, then two cannot hold, and vice versa, if two holds, then one cannot hold. So let's first show that if we are in case 1, then you cannot be in case 2. So 2 cannot hold. Now 1 holding means that p divides n, so there exists some integer q such that n is equal to pq. But if the second statement also holds, then you have that the GCD of P and N is equal to 1, but this N is PQ, and we know that this GCD is the same as the one we obtain if I change the second argument by adding a integer multiple of the first one. So what I'll do is I'll add to this N minus Q times P, and then the GCD does not change. But this is just 0 because n is pq, so we get GCD of p comma 0, which is equal to p, and p being a prime number, we know it is strictly bigger than 1, so we get the contradiction that 1 is strictly bigger than 1, so obviously this cannot hold. So this contradiction arose because we assumed that 2 also holds, so 2 cannot hold. So we have managed to show that if we are in case 1, then this statement 2 cannot hold. And the contrapositive of this is that if 2 holds, then 1 cannot hold. And so we have shown that these two statements are mutually exclusive. We will now show the theorem which says that if p is a prime number and a and b are integers such that p divides their product, then p divides a or p divides b. So p has to divide one of them. So this suggests that the prime numbers are like the atoms, they cannot be further divided, because it's not the case that p can be factored into two smaller factors so that one of them will divide A and the other one will divide B, and then P doesn't have to divide any of them. No, it's the case that P has to divide one of them. So let's prove this now. Let's first consider the case that P divides A, then we already have one of these two cases happening, and so we are done. And let's now suppose that P does not divide A, but then since P is prime, then we know that the greatest common divisor of P and A is equal to 1 by the theorem that we have just proved. And so we have that P and A are coprime. But we have also seen the theorem which says that if A and B are coprime and A divides the product of B with some C, then A has to divide C. So if we apply it over here, we know that P divides AB, and we have just discovered that P and A are coprime in this case. So then it has to be the case that P divides B. So we have got that. And so when P does not divide A, it has to divide B. So this completes the proof of this theorem. So again, to repeat, it says that if a prime number divides a product, then the prime number has to divide at least one of the two factors. We now generalize the theorem that we have just learned to more than two factors. So we will derive the following corollary from the theorem that we have just learned, that if P is a prime number which divides the product of n numbers where n is bigger than or equal to 2, then P has to divide at least one of them. So P divides AK for some k which is bigger than or equal to 1 and less than or equal to n. So we will prove this by induction on the number of factors. The base case is when n is equal to 2, and that we have just covered in the theorem. And let us suppose that we have proved this statement for some natural number n where n is bigger than or equal to 2. And now let's suppose that we have n plus 1 factors. So let's suppose that P divides a1 all the way up till an times an plus 1. But this you can view as the product of two things, a1 to an times an plus 1. And since P is a prime and it's dividing the product of two numbers, it has to divide at least one of them. So we have that with the n equal to 2 case, P divides a1 to an or P divides an plus 1. Now if P divides an plus 1, well, it's dividing one of the factors, and so we are done. And in the case when P divides a1 to an, then by the induction hypothesis, since we were assuming that this is true for this n, it follows that P has to divide at least one of these a1 to an. So P divides ak for some k bigger than or equal to 1 and less than or equal to n. And so in this case also we have that P divides one of these factors. And so we have shown that the result also holds for n plus 1. So by the principle of induction, this holds for all the natural numbers n bigger than or equal to 2. We will soon use this result. The next task at hand is to prove the fundamental theorem of arithmetic, which is an important theorem in mathematics, and it says that every non-zero integer can be written uniquely as a product of primes. So the only non-uniqueness is in the order of multiplication of the primes. That can be swapped, but other than that, it's unique. So before we give the precise statement of this fundamental theorem of arithmetic, let us see some concrete examples to see that indeed this happens to be the case. So let's start with 600, and we would like to express it as a product of primes. Now the way to do this is you keep extracting prime factors. So it's clear that this is divisible by 2, and in fact 600 is 2 times 300, and then 300 is again divisible by 2, so you can write this 300 as 2 times 150. This is again divisible by 2, so 150 is 2 times 75. And this 75 we note is divisible by 3, it's 3 times 25, and then this 25 is 5 times 5. And now we cannot further subdivide because each of these factors is a prime, so that cannot be further split into non-trivial factors. So you have got 2 to the power 3, the next prime 3 to the power 1, and then 5 to the power 2. So 600 is indeed expressible as a product of primes. If the number happens to be negative, then of course, since all the prime numbers are positive, we will need an extra -1, and once you have that, then I'm left with 693, and we repeat the process. So for 693, an obvious divisor is 3, so this is 3 times 231, and this is 3, 4, 5, 6, so this sum is again divisible by 3, so this is divisible by 3. And in fact, if you do the division, you will find that this is 3 times 77, and 77 has the obvious prime factors 7 and 11. And so we have ended up with -1 times 3 times 3 times 7 times 11. And all of these are primes, so they cannot be further split into non-trivial factors. So we have got -1 times 3 square times 7 1 times 11 to the power 1. And all the primes which are missing over here, you can introduce them with the power 0. So for example, you can also write this as 2 to the power 0, the next prime is 3 to the power 2, then 5 is missing, so 5 to the power 0, which is 1, and then 7 to the power 1, and then the next prime is 11 to the power 1. So also negative integers with an extra minus can be expressed as a product of prime numbers. So the fundamental theorem of arithmetic says that if you have any non-zero integer, then you can write it as a product of primes, and if the integer is negative, then we will have an extra -1. So the statement is that n can be written as c multiplied by p1 to pk, where this c can be plus or -1 depending on whether this n is positive or negative. And also this expression is unique, so all you can do is swap these primes around, but other than that the same primes will appear the same number of times. Okay, now we also remark that if in this list of non-zero integers are the integers +1 and -1, and since the primes are all strictly bigger than 1, in these two cases these won't arise, it's just 1 over there. And rather than make exceptions for these two cases each time, we just imagine that in that case too you have n is equal to c times this empty product where these don't appear at all and are replaced by 1. Okay, and the reason is because, well, it's convenient to think about it in this way rather than make exceptions, because in the proof that we will give, otherwise we'll have to keep considering cases. So it's much more slicker or more efficient to say that, well, for all non-zero integers you can always split it like this, but of course if n is equal to plus or minus 1, then this is an empty product and then it is taken to be equal to 1, so no primes appear there then. Okay, so we are now ready to give the statement of the fundamental theorem of arithmetic. So here is the statement of the fundamental theorem of arithmetic. It says that every integer n not equal to 0 can be written as a product n equal to c times p1 to pk, where the c is equal to +1 or -1 and p1 to pk are all primes. And as we mentioned before, if the n is plus or minus 1, then there are no primes which appear here, and this product is the empty product which is taken as 1. And moreover, this expression is unique except for the ordering of the primes. Indeed, integer multiplication is commutative, so you can arrange these in any order you like, but other than that, this is unique. So the same primes will occur the same number of times. Let us now prove the fundamental theorem of arithmetic, and the plan today is just to prove the existence of this factorization, but next time we will also show the uniqueness. So here is the proof of the existence part of the fundamental theorem of arithmetic, and let us assume first that the given non-zero integer is actually positive, so that this n is a natural number, and later we'll also consider the case when the integer is negative, so that -n is then a natural number. But let's begin with n being a natural number. And this proof of the existence part we will do by induction on this n. So the base case is when n is equal to 1, And in that case, we know that the claim is true because 1 can be written as 1 times 1. So this C is equal to 1, and this 1 is the case when there are no primes at all, so that you have the empty product. So in this case, the claim is true. And let us now suppose that the claim is true for all the natural numbers which are less than or equal to n, where n is some natural number. So we'll use strong induction. Now we want to show that the claim is true for n plus 1. Now we have only two possible cases, that n plus 1 is prime or n plus 1 is not prime. In the case that n plus 1 is prime, then we are done, because n plus 1 can simply be written as 1 times n plus 1. Now here is a prime and here is C, which is equal to 1. So the claim is true in this case. Now let us suppose that n plus 1 is not prime. In that case, it has a positive divisor which is not 1 or n plus 1. Okay, and let's call this divisor as D. So you can write n plus 1 as D times m. Now since D is not 1 or n plus 1, m cannot be 1 or n plus 1 either, because if m is equal to 1, then D will be n plus 1, which we know is not true. And if m is equal to n plus 1, then by the cancellation rule, D will be forced to be 1, but we know that D is not equal to 1 either. So this m is not 1 or n plus 1. So then we have that since D is not equal to 1 and it's a natural number, it's bigger than 1, and by multiplying both sides by this m, we have that the inequality is preserved, but this m times D is n plus 1 and m times 1 is m, which we know is not equal to 1, so it's bigger than 1. So you have got that m is strictly bigger than 1 and strictly less than n plus 1. Okay, so we have m is bigger than 1 and less than n plus 1, and the same thing is also true with this D, because we know that 1 is strictly less than m, and by multiplying both sides by D, you get, well, D times m is equal to n plus 1, and D times 1 is D, which we know is bigger than 1. So you have got that D is strictly bigger than 1 and strictly less than n plus 1. So D is also in between these two. But that means that this m and D are strictly bigger than 1 and they are less than or equal to n. Okay, so this m and D are natural numbers which are less than or equal to n. So by the induction hypothesis, we know that they can be expressed as a product of primes, and the C is equal to 1 because m and D are both positive, right? And also we know that there are primes because this m is bigger than 1 and this D is bigger than 1. So you have that m is equal to P1 times Pk, some k primes might be there, and D is some Q1 to QL for some L primes Q1 to QL. So then n plus 1, which is D times m, well, m is the product of these primes and D is the product of these primes. So we have been able to express this n plus 1 as a product of primes. So this completes the induction step, and so by the principle of strong induction, we have that this is true for every natural number n. So far we have covered the case when the integer is positive. Now let us consider the case when n is non-zero integer but negative. So we have already seen the proof of existence when n is a positive integer, and now when n is a negative integer, then we know that minus n is a positive integer, so minus n is a natural number. And so by the previous part, we know that this minus n can be expressed as a product of primes, P1 to Pk, and by multiplying throughout by minus 1, we get that n is equal to minus 1 times P1 to Pk, and then you have got this C is minus 1 and you have a product of primes. So the claim is also true in this case. So it remains to show uniqueness, which we will do next time. We'll begin the lecture with that, and we will also see how to do the computation of the greatest common divisor using prime factorization. So we have learned Euclid's algorithm for calculating the greatest common divisor, but we will also see another method using the prime factorization.